Hey everyone, we're gonna have our second 12-1 video, and today it focuses on partial sums. So the first part of 12.1 we talked about sequences, kind of a pattern of numbers, a list of numbers, and the partial sums of a sequence are defined as you can see in this blue box here. So we call S1 a partial sum, and it's the first partial sum. And it literally just means the first term of that sequence, A1, A2, A3, A4. If we do S2, that's the sum of the first two terms, A1 plus A2. And you can see that pattern building. S sub 3 is how you say it, or the third partial sum is A1 plus A2 plus A3, and so on and so forth until we get to the nth partial sum. And that means the sum of the first n terms. So it sort of seems like it's like maybe you might call it an infinite sum, but it's not. It has a stopping point. Whatever n is the stopping point. So it's the sum of first n terms. Okay. And we call that the nth partial sum. So let's take a look at an example. Find the first four partial sums and the nth partial sum for a sub n equals 2n minus 1. So to do this, I'm going to list out actually our first four terms of a sub n. So we have a sub 1 equals 2 times 1 minus 1, which equals 1. And then a sub 2, I'm not going to write it out every time. 2 times 2, 4 minus 1 is 3. And then a sub 3 would be 6 minus 1 is 5. A sub 4 would be 7. So notice like we could keep that pattern going, and the nth term is 2n minus 1. It's the odd numbers, 1, 3, 5, 7. We keep going, 9, So if I want to find the first four partial sums, I have s sub 1 is literally the sum of the first term, which is just 1. Cool. S sub 2, 1 plus the second term, 3, and that equals 4. The third partial sum would be 1 plus 3 plus 5. So that's 9. S sub 4, 1 plus 3 plus 5 plus 7 gives me 16. So if I kept that pattern going, the nth partial sum it'd be 1 plus 3 plus 5 plus 7 plus 9 plus all the way until we got to 2n minus 1. And that sum, well, there seems to be a pattern here. We go 1, then 4, then 9, then 16. If we went to the next one, s sub 5, the fifth partial sum, 16 plus 9 is 25. Those numbers are familiar. That's the perfect squares. So the sum is n squared. The nth partial sum is n squared. That's kind of cool. If I wanted to find the sum of the first 12 odd numbers, it would be 12 squared. How cool is that? So that's our first example here. I've got the second one mostly filled out already just to save a little bit of time. First four partial sums and the nth partial sum for 1 over n plus 1 minus 1 over n plus 2. So off to the left here, I've got those first four terms written out. I didn't simplify them for a reason. And then when we find our first four partial sums, so I do that first term, which, okay, now I can simplify it, you get 1/6. Then for the second sum, I'm going to do 1/2 minus 1/3 plus 1/3 minus 1/4. Well, something kind of interesting happens there. The minus 1/3 and the plus 1/3 would cancel out. So we really get 1/2 minus 1/4, which is 1/4. As that continues here, I see that same pattern where all this inside stuff cancels out. So for s sub 3, I get 1/2 minus 1/5, which is 3/10. And then for the fourth partial sum, I end up with 1/2 minus 1/6 equals 1/3. And so here, I'm looking at this, 1/6, 1/4, 3/10, 1/3. I don't see any pattern there. Like the one before, we had those perfect squares. It was really easy to see the pattern. Here, not so much. But let's look instead at the unsimplified version. I ended up with 1/2 minus 1/3 in the first one. And then it was 1/2 minus 1/4. And then it was 1/2 minus 1/5. And then it was 1/2 minus 1/6. That seems to be a pattern. And so my nth term always seems to be 1/2 minus 1 over something. Well, that 1 over something, let's see. It was 1 over 3, 4, 5, 6. So it's going up by 1 every time, which it, like n goes up by 1. So it's involving n, and it's always 2 more than n. 2, 4, 3, 5, 4, 6. So it's 1 over 2 minus 1 over n plus 2. And that's our sum of the first n terms, is what we would get. Let's move on to something called sigma notation, also known as summation notation, which is kind of a fun way to say it. It's called sigma notation because it uses the Greek letter sigma. It's a capital. And the way to draw it, because I always used to screw it up, and then I learned how to draw it, and now I don't screw it up anymore. It's the top is flat. So start with a flat top, and then just finish the rest of it's easy. You can, if you want to get real fancy, put the little like hitches at the end, but you don't have to. The mistake you make is if you don't make the top flat, you end up like with that, and that doesn't look any good. So don't do that. Start with a flat top. And you've got these kind of key parts to it that it talks about over here. On the bottom, we have usually a little equation, k equals 1. That tells us we're starting with the letter k equals 1. Well, where's k involved? It's here. This is our, basically a formula that'll involve k or whatever variable is on the bottom. And on the top, it'll tell us where to end, k equals n, or whatever number is there. The sigma stands for sum, so it means to add it up. And so if you look at this formula, basically, we would say, read this as the sum from k equals 1 to n of a sub k. And so that means I plug in 1 for k, and then plus, and then I plug in 2 for k, and then 3, and then 4, and I keep plugging in numbers for k until I get to the last one, which is the number on top, in this case n. So let's see what that looks like in an example. Problem 3, find each sum. So here we have the sum from k equals 5 to 9 of k. So that literally means I'm going to start with k equals 5, and then plus, and I'm just going to keep increasing k by 1, 6, 7, 8, 9, until I reach 9. And then we would add that all up. What do we get? That's 11, and 9 is 20, and 15 is 35. So my answer is 35 there. You don't always have to use k. For the next problem here, we see it uses I. So not the imaginary number, just a kind of a counter variable I. And so in this one, we're starting at I equals 1 all the way up to I equals 3. And the formula is I times negative 2 to the I. So first I plug in 1. 1 times negative 2 to the 1. Plus 2 times negative 2 to the 2. Plus 3 times negative 2 to the third. This one becomes negative 2 plus 8 plus 24, negative 24. And that gives me negative 6 and negative 24. That's negative 30. So the answer to B is negative 30. C goes from 3 to 200 of 5. The sum of 5. What does that mean? Well, it means there's no k involved. So it just means I'm literally going to add 5 over and over again until I get to k equals 200. So let's see. We got to figure this out. This one is k equals 3, 4, 5, 6, skip a few, 200. So how many of those 5s are there actually there? Well, let's see. If it was, what if we just stopped there? That would have been k equals 3 to 6, and that was 4 5s. If we had stopped a little earlier, if we had stopped here, 3 to 5 was 3 5s. So I can subtract, like 6 minus 3 is 3, but I had 4 5s to add up. 5 minus 3 is 2, but I had 3 5s to add up. So it's always one more than the top number minus the bottom number. One, spell 1 with the number 1 in front. One more than top minus bottom. So we've got 198. 200 minus 3 is 197, but we need one more. 198 5s. So the answer to this is going to be 198 times 5, which should be 990, I think, right? Because 200 times 5 would be 1,000, so we're 10 short of 1,000. There we go. All right, almost done here. Last two problems. We're actually going backwards. We're going to write in summation notation. So here we just have to try to find the pattern. Okay. So, and it says to write it in two different ways. We're going to talk about why and how you could do that. So start with your sigma, flat top. And my pattern here, I go 3, 4, 5, 6, 7, 8, 9 to the 4th. So it seems like we're raising some number to the 4th. So if we just said k to the 4th, we would have to start with k equals 3, and we would go all the way until k equaled 9. That's it. Easy enough. Another way to write it would be instead to say I'm going to start at k equals 1. It's still going to be something to the 4th, but this time my first thing to the 4th is 3. So if I just started with k, I would have 1, so I need to get up to 3, so I'd have k plus 2 to the 4th. And here, I guess we would have to kind of go with that same idea. I'm adding up 1, 2, 3, 4, 5, 6, 7 terms. And so I would end up with going from k equals 1 to 7. Or we could have figured that out from 9 minus 3 was 6, and adding one more is 7. All right, last problem. This one looks a little complicated. Alternating signs means we should have a -1 involved. We saw that in the other video. And I want the first one to be positive. So if I plug in like 1 for n, or k, or whatever letter we use, that would make the first one negative. So I'm going to either do n minus 1 or n plus 1. Okay. So let's see. I've got the sum from k equals and let's see. What pattern do you notice? Well, I notice the top sure looks like k. 1, 2, 3, 4, 5, 6, 7. So the top appears to just be k. The bottom is 1, 2, 4, 8, 16, 32, 64. Oh, that is 2 to a power. If we just did 2 to the k, I would get, and I started at k equals 1, I would get 2 to the first, but I want 2 to the 0 to start, so I need k minus 1. All that has to alternate, so I'm going to then multiply it by our negative 1 to the, and I have to put k minus 1 because I used k. And how many terms do we have? 1 all the way up to 9, so it's a 9. Okay. Yeah, this one, let's just write it this one way. Probably not the best option for doing it a different way, but basically you just shift your k and your k minus 1 around. All right, that is all. Thanks for watching.